think that will be us for this talk. So, welcome everyone. Thank you for joining us. This time I'll be, again, a speed talker. Yet again, I will be joined by Juan from Gali and Pierre-Loup from Valve. We're going to talk today about the releasing and testing process of Mesa. We're going to cover a bit of historical talk and actual current state. So, obviously, details about myself. Should have mentioned Pierre-Loup here, sorry. Myself, I'm a software engineer at Collabora, working on Mesa since 2011. Juan is working since 2015. He's from Gali. Here is our agenda. We're going to give you a bit of information about Mesa, sort of what's in it, the actual releases we have, how we present them at the moment. We're going to give you some historical talk and how things have evolved in terms of releasing, documentation, and so on. Additionally, we're going to cover the current process. I believe around that stage, Juan is going to join me. He's going to talk about what he's doing at the moment, the test systems we use, some of the stuff they've been doing in the GitLab CI, and at the very end, Pierre-Loup is going to mention about the work they've been doing with LunarG. So introduction, as you know, Mesa is old. Started back in 1993. You can describe it as a framework of drivers, has quite a few of those. This is a small set of APIs that are implemented in Mesa, and as you can see, they are still sizable. Additionally, we have drivers that cover multiple vendors, from desktop ones such as Intel, AMD, and Nvidia, to ARM ones such as Qualcomm, Broadcom, etc. Keep that in mind that obviously some drivers are officially supported by the corresponding vendors, while others are not. Oh, to top it up, we have 4 software drivers. Okay, so the releases, we have 2 types of releases. One of them are feature, other are bug fix releases. The feature releases are roughly 4 a year, so that's one every 3 months or so. We start that by branching off from master. We create a branch point. We apply patches more or less every day, up to a couple of days. We roll a release candidate every week up to the eventual release. We try to keep that around 4 weeks, although sometimes things run off more since there are regressions. We do our best to provide a tracker where the different teams can list their blockers so that we can easily track both on our end and theirs what's happening, and obviously provide some clarity for every distribution and user interested. Important part is we make no changes whatsoever from the last RC to the actual 0.0 release, so that nothing hidden happens. Everything's transparent and clear. On the bug fix releases, we have a rule: no features whatsoever. We may add PCIs, which is effectively hardware enablement, but no functional changes whatsoever. We try to keep those every 2 weeks, every fortnight. And as I said, unfortunately, we may have the odd delay here and there. I believe Juan is going to cover some of the obstacles that may cause those. And obviously, we cover bug fix releases for the whole period of the actual feature release. That means we will provide bug fix releases for a period of roughly 3 months. A bit of origin and the process, as I mentioned, started with Brian Paul a while ago. Obviously, in the very early stages, there's a lot of development. There is no documentation. There is no actual strict process. Obviously, most people were hacking for fun. Around Mesa 3.4, things started forming in the ways of having distinct releases, features, and etc. As you can see, there was still far and few between. And slowly things have improved. I believe around 2009, Ian Romanek from Intel steps in, helps out a lot. He improves the quality and frequencies, as you can see here. And most importantly, he provides a clear tag, a clear way to nominate patches. Since up to that point, it was either up to the individual to poke Brian, or via the side channels, which may not be always clear and transparent. Or they might be, but it would be fairly hard to find out. Shortly afterwards, Carl Wirth from Intel steps in to help improve the bug fix releases. He does that by, number one, ensuring the volume and the frequency of that. Two is introduces the CC Mesa stable tag and deprecates the earlier note. For those of you who have done some kernel work, you know that the kernel has a similar notation and it operates the exact same way, such that the release manager can easily filter those patches, apply them. Additionally, you have a separate mailing list that is a lot lower volume, and people can nominate at later stage. They can comment in there without the risk of their information getting buried in the volumes you get otherwise on a development mailing list. He also formulates the acceptance criteria, which are also based on the kernel style. He also, at the very end, he documents the process he was using throughout his period before handing it over to me. So I've been doing that more or less since 2014. My main focus was to improve the process in multiple ways. Number one is to ensure that things are documented. Number two is to ensure wide testing. And number three is scalability. First thing that I mentioned over there is to make sure that you can utilize more than one core. When I started, you can build Mesa only with J1. We didn't build most of Mesa. And today, we more or less built everything with a few very small exceptions. Additionally, originally, things were built only on the release manager's laptop or machine. These days, obviously, we have Travis, behaviour. Personally, I built with and without DRM because of some interesting interactions. I also built with MinGW. I believe other guys have extra local testing they perform. As I mentioned, the release and documentation was a fairly important part since as I started let's put it this way, all the information was nicely clumped up in a single HTML file that was like, I don't know, 10 pages long. So I split that up, I enhanced it a fair bit, I cleared up and simplified actually a couple of cases where the developers did not agree upon the acceptance criteria. Additionally, there was a fair bit of work on improving the tooling we use, such that, well, we make typos, we make mistakes. Quite often we'll mistypo, let's say, Mesa stereo to Mesa dev, or we'll, instead of CC, we'll write something else, and those won't flag up. So I fixed a few bugs here and there, and the numbers have improved. Additionally, I've adopted the fixes tag, which is also from the kernel. It provides a short SHA with the actual title, such that if one of those are wrong, we can use the other to infer and to find the exact commit, which has happened. The next step is Andres and Juan from Igalia started helping out from 17.0. Initially, they were helping with bug fix releases. These days, they're helping out pretty much everything. Since we moved from a single individual to a group of three, unfortunately, there were some misunderstandings who's doing what. So it became kind of obvious that we want to have information about all of that in public, normally discussed on the mailing list, so that everyone is aware of what's happening. There's nothing hidden. There's no shenanigans or anything. The guys, I believe, Andres improved our scripts even further, where people will unfortunately make other mistakes. So it managed to catch even more fixes that should land, which was great. And as I said, they've been working on GitLab CI, something Juan will cover in a moment. Our latest addition to the pool is Dylan from Intel, who's been working since Mesa 18.1, I believe. He's our resident Python expert. He's been helping with Mesa and Piglet and a lot of Python code, improving things drastically. Additionally, there's a very good part that has direct access to the Intel CI, which, as I said, we'll briefly cover later and later with the talks from Mark James. There is a very interesting topic every now and then. What is this CC? What is fixes? Which one should I use? Should I bother? Should I not bother? What's gonna happen? Is my fix gonna be dropped if I change something? What can I remove? What can't I remove? So we have some points here, as you can see, as an outline. In general, Mesa Stable helps us a lot. It is something you'd use if you do not know when the problem occurred. Would that be because it's very complex, or would that be because, let's say, historically it's impossible to figure out? Or would that be because it just was broken from so many points and just impossible to point out to a particular commit? The fixes itself is, as I said, it's a very nice consistent notation, which I believe on its own is worth using pretty much anywhere and everywhere, anywhere and pretty much all the time. The idea is that it provides a clear and consistent way for you and for your fellow colleagues to know when you're referring to a commit. Throughout my experience, I've seen over 3 different notations in the kernel and over how many, I don't know, notation elsewhere, which makes a very hard reading experience for non-experts in the actual code base. And as I pointed out, it's fairly easy for the maintainer to, based on that information, it's very easy for the maintainer to pick and apply the patch only where it's needed. By default, we just throw the fixes tag. You don't need to worry if your patch applies to any stable release or not. Another very important part is that quite often people will need to pick up Mesa, would that be stable or an arbitrary point, and they will want to know when things are fixed. So by using this particular notation, they can themselves internally run through our scripts, do additional extra checks, and ensure that they do not hit bugs. The very same bugs fixed with the patches. Obviously, the most important question, when will and how will my patch get dropped? Our intention is to not drop anything silently. Even if you self-reject patches, we have this notation of self-rejection, which if we have some time at the very end, I would like to see how many people are using and how many people think we should keep or drop, since that is causing a bit of confusion every now and then. Our best intent is to apply everything, but as I said, we're human. Sometimes, let's say, there is a typo in the nomination. Sometimes we miss something. Sometimes, mistakes happen. Even with the best of tooling, there will be mistakes. The important part at the very bottom is if by any chance your patch is deemed, let's say, not worthy enough, or you did not adhere to the acceptance criteria and your patch is rejected, you will be contacted. You will be contacted via email. Quite often you might be poked over IRC, and obviously you can say, yes, agree with the decision, or oh, my bad, I made a typo, and yes, it's not applicable at all, or it's not applicable here, it's applicable there. So we can just double check everything for you, ensure that you have the best actual fixes, the best drivers, and having all the fixes applicable to where they need it. I believe at this point, Juan is going to join me. He's going to talk about the current way of handling, and shortly afterward, as I said, Pierre-Louis is going to talk. Thank you.
Thank you, Mir. Okay. So after all the process that Emil was describing, now we have a candidate release. And now the point is the release will work, this release? Will have any failures? So basically, the first thing we need actually to solve is this release going to be buildable? Because in Mesa, we have different combinations of different options. For instance, we have different build tools, like AutoTools, Sconce, and Meson. And then, for instance, in the case of the Gallium drivers, we depend on the LLVM, and there is several versions of the LLVM with different APIs. So when you make all the combinations, you need to be sure that everything works fine. And of course, we do, as release manager, we try to do all these combinations locally, but the thing is that this should be detected as soon as possible, even before the release in the master branch. So in this case, what we are using is a combination of the GitHub plus Travis plus AP behaviour. So every time we push a patch on the master, this is a hook that push it to GitHub, and the GitHub triggers a build in Travis that basically builds different combinations of different build systems and LVM, and also a behaviour for the Windows system. So in the right screen, you see an output of the Travis running one of these pushes. As you, well, probably you can't see, but here there is different combinations of different tools, and in green if the builds or not. So this is a first step, but of course it's not enough, because you can have something that is buildable, but then you are going to use it, and is completely broken. So we need to do testing, and in this case, the official process right now basically is doing manual testing. So before doing the release, now that everything is buildable, we just run different test suites, games, or 3D applications. But of course, it's not scalable. So we need some kind of automated testing. So here we have two types of different test systems we can do. One is the unit testing. It means that you have test units that try to test if a specific feature or works or not. So you run the test, and if it fails, it's a regression. If it passes, it's a success. And then they have the functional testing, which means that's like running a game and check for any problem on this. So we'll focus on the functional testing at the end, now focusing on the unit testing. Thing is that basically we are using the Mesa, the Intel CI system for Mesa. I'm not going to enter in details here because there is a nice talk later by Mark and Clayton. But just to mention that there is a very, very powerful and very useful CI system, and it's used not only for release managers, but also as developers. You use it a lot. And it's a basic tool that for us is a must to pass this Intel CI. Thing is that running this Intel CI takes a lot of time. It uses a lot of hardware and resources. So it has several implications. One of them is that when we start this process, sometimes some patches arrives, last-minute patches, and we usually try to enqueue these patches for the next releases because we don't want to repeat again the test process because it will be delayed the release for sure. So we only do that if there is a very critical patch that is fixing a real problem in the current release. So that means that we apply in the queue and resume all the work and restart, and probably we need to delay the release one day. Otherwise, we just mark it as nominated patches. Will be added in the queue for the next release, but we inform the authors that these are good patches, but we will not enter in this process. This is done in the email in the section nominated patches, which basically means that your patch is fine, but we can't. It arrives late. The other thing is that, as I said, it takes a lot of time, and basically we don't want to send anything to the Intel CI before doing a previous quality checking, which means that basically that we want to do first running our tests locally, very limited kind of tests, and then if everything is fine, then we submit it to the Intel CI. So for doing this testing, as I said, so far we are using the combination of Travis CI and API. As you might notice this system only allows you to build to test the building of the release, but it can't test because at the end you need real hardware to do the testing. And the Travis and API behaviour is using virtual hosts which don't have a real hardware. Thing is, besides that, now in Free Desktop we have GitLab, which was nicely explained by Daniel in the previous talk. And among other features, it has the continuous integration system, its own CI. So basically, we don't need to rely on Travis CI and GitHub, but we can use the GitLab system. And has other many features that we will explain later that it helps us to improve the test system. So even before that Free Desktop moved to GitLab, we were using inside the Galia for the releases, we were using the GitLab.com to do the build and testing system before sending to Intel. So as I said, it was only used for preparing the releases, and the idea is okay, we have add patches on the candidate release, push it to GitLab.com, it runs a lot of tests, it tell us, okay, this is our regression here, it's not a regression. If everything is fine, we continue, and when we have a real good, or at least some quality candidate release, then we push to the Intel CI. So basically, we use this more or less every day or every 2 days, and then before sending the pre-announcement, we submit everything to the Intel CI, which it will take time, but it will give, okay, this is correct. So this way, we don't waste time from Intel people to do this testing. So when we were moving to the GitLab CI, we have something we would like to change. It was, with Travis, basically the idea was, okay, you run you take your code, you build in Travis, everything is fine. Now, for testing, you take the code, you clone the code in each of the hosts that are you going to test. You build Mesa there, then you build the test suite you are going to use in each of the hosts, and then you test. And really, if you think about it, you are wasting a lot of time because you are building the same thing several times when just building once will be enough. And this is especially important when you use for testing hosts that are not so powerful. Like you have some NUC that is not very powerful, but are cheap, and you can have different cards. So basically, you want just to only use it for testing, not for running, for building Mesa. And the other thing is that, and the happened is that on each host, sometimes you have different versions of the software, like different distros or different, even in the same distro, different versions of the distro. And sometimes you have some libraries installed on one system, other libraries in other system that enable some features. And then when you are trying to compare, there is like these different softwares like influencing in the results. So what we like is, okay, let's build the same thing once and just take it, everything, you mean Mesa and all dependencies, put it in the test system and run out the tests. So the only difference is about, well, beside the kernel, the only difference is that is only the hardware. All the software is the same. So thinking about this, also there is the other problem, which is, well, we need a way of how to have these encapsulate binaries in easy to distribute system. And here, and Docker really helps a lot using containers. GitLab has a nice integration with Docker. So Docker is a really good way to just to put your blob already built in a very contained system, and then using the register of GitLab, very easy to pull it and install on all the systems. And the other thing that is nice as Docker is, the build of Docker is contained in a single Docker file, or it's very easy to reproduce locally the containers. And this is something that as release manager we do a lot of times when we find problems. We just take the container and sometimes we rebuild the container locally and we get exactly the same version of the container. So we are using the same approach as in Travis, that is, check different combinations of the build tools and the LLVM versions, just to ensure that everything builds. In this case, we are not while we are using Docker image, we are not using Docker itself for building. The thing is that on one side, this lot of combinations makes quite difficult to write a Docker file that is simple enough to combine those different options, and the Docker file syntax is quite rigid. On the other hand, is that to speed up the building, we want to cache the build using Gcache or something like that. And in Docker, unfortunately, you can't build external directories on build time. So it's basically makes it difficult to have a way of improving the build system. So here we are using Rocker, which basically is a Go tool. It's a single binary tool, which is you can download it, and you don't need any dependencies, so it's very easy to use in any distro. And basically, it provides these two features. It provides templating, and it provides mounting on build time. So with this, we just speed up the system and make the things easier. So the idea is that we create here different image. At the end, all the images contain the same software, that is the drivers we want to test, but it does using different combinations on using scones or using auto tools with different LLVM. In order to test, only once is required, only one of these images. So basically, we just drop the other image. They are only used for checking if things build correctly. And we push to the registry the image that contains all the drivers you want to test. Another thing we were doing regarding the Travis is that, as you know, in Mesa we have the minimum dependencies to build Mesa, and it is very nice to build Mesa using these minimum dependencies because it's easy to detect that if the dependency is too old, just to boom up in the build tool to say, okay, now I need this library version +1. But of course, the problem is that you are installing the dependencies, all the package in Debian, everything, every time you make a push. And it takes a lot of time. So as in Docker, basically you can start from init image and then add your code and like in this case, Mesa, instead of starting from Ubuntu, which is what Travis is doing actually, we just create a base image system. And this base image system is like a Docker image that contains everything you need to build Mesa. And this only built once. Well, it's only built once except if you change dependencies. So if you change dependencies, we create another base image. And so basically, it speeds up the system because you don't need to rebuild all the time the image. And also, as part of the base image are packaged from Ubuntu, in this case, we just force a rebuild once per week. So we ensure that the base image is always updated with the last versions of the distribution package. So here, there is, this is the pipeline. In the first two columns, well, the first column is the base system, which just takes an Ubuntu distro and install all dependencies, either from package or from the source code, like we are doing in Travis. Then from that image, we create several different images with different versions of LLVM. The reason why we separate those images is on one side, because this way we reduce the size of the image. When you want to test against LLVM 5.0, you don't need to pull all the versions of LLVM. That's on one side. And the other is that we ensure that in that image, we only have LLVM 5.0 and not other versions that could mess up the system. So, as I said, this system basically is just build once. Every time you push, it checks if there is changes in dependencies. If not, we just go out to the next step. And the next step basically is building Mesa. Well, basically it's building different combinations of the auto tools, the build tools like scones, LLVM, so on, and different versions of LLVM. So when this finalizes, actually we only keep one of these images. I think it's the first one, is pushed to the GitLab registry. The other one is just removed. We added another step, which is, there is one of the job, which is the this check job. Basically, this check, as you can figure out, just runs this check, which creates the a candidate release tarball. This check, what it does is create the tarball, and then it tries if it builds with make. But as I said, we have other build tools. So what we do is in the tarball stage with the fourth one, basically we take this the tarball generated from the check, and we just try to rebuild it using all the build tools. So we ensure that, of course, nothing is missing in the final tarball. Okay, so this is for building, and now we need the next step, which is now how to test. And as I said, we need real hardware to do the testing. And this is where really GitLab shines, because in GitLab, usually they provide several runners that is choosing to run your jobs, but you can provide your own runner. If you have your project, you can go there and say, okay, I want my own runner, which basically means I will take my host or laptop or whatever you want and say, okay, I want to use my host to run jobs. And of course, well, the thing is that the way it works basically is like, well, GitLab provides different ways of running. The case we use is using a combination of Docker. That is, we just, in GitLab running is run by using Docker mounting the graphics device. So we have access to the hardware, to the graphics hardware. And then basically when the test is going to start, it takes this image from the GitLab registry, which is the image which contains Mesa, mounts with these options, and then runs the test system. The way to tell, okay, I want to use this specific hardware using basically tags. So, for instance, we have a Skylake host. Then we annotated in the Docker, okay, this is a host used for testing. And I add tags like test with OpenGL, test with Vulkan, this is Skylake. And then in the jobs, we use also tags to match. So for instance, I say, okay, for the testing, I want to use a Skylake machine. So we will check for a runner that have a Skylake tag. Could be, you can have several hosts, take the free ones, and run the test. So how this is basically working? The thing is that you run the Mesa. When it finalizes, it triggers a build on the test suite you want to test. Basically, we have all the test suites in the GitLab repository. So basically, we're using the same approach as in this case for Mesa. So as an example, the test system basically triggers which is the fifth one, triggers test Crucible or OpenGL CTS from ChromeOS, Vulkan CTS, or Pilit. So the output of these triggers, which is basically calling an API, a webhook, creates these downstreams projects, which basically is just running those external projects. So when you click on one of them, which is something nice from GitLab, in this case, I click on Pilit, I can browse to the Pilit repository and see what is the building happening. So it shows me that this build is coming from this job in Mesa. So what it does here is just take this image created in this Mesa, creates another image adding Pilit. As I said, this is the build step, and then it runs the tests. And running the tests is running in with several drivers, and it just takes the image with the build and start to execute it. So basically, this shows in green when the test suite is finalized, or in red if there was some problem and the test suite couldn't be run. Now, for knowing the regressions, basically we are running all this test system test suite, sorry, are integrated with Piglit. So we use Piglit just to create nice HTML files, and which are stored as an artifact in GitLab, which is another feature. And the thing is that in order to know if there is problem or not, what we do is just the same pipeline you see before are used for when we make our release, but we use a very simplified version of this pipeline. So this pipeline basically does the same and generates the Piglit results. And those Piglit results are used as reference tests when we use, in this case, the pro-release version. So basically, we just need to only know if this is some problem or not. In this case, for instance, well, I don't know if you can see it, but here is the output on the black screen. And then in the right, there is the artifact will be removed in 3 months. You can download the artifact, which is basically the result of the Piglit, or you can browse on it. You click on the browse, and you go through and see the results of the XML, sorry, the HTML. So ignore the names of the columns, but the thing is that we have the last release version on one side and the current candidate release version. So in this case, there are 3 regressions. So basically, one go there and check what happened. Maybe it could be a false positive and so on. So doing that, basically, we have a minimum quality system that we know that the candidate release is, I mean, it has some, at least some quality. So after do that, we just submit the candidate to the Intel CI system just to make a more exhaustive test. Because there are some times that there are more combinations like using 32 bits and things like that we are not testing. But at least we have some kind of quality, and it really helps to Intel and for us. So that's for unit testing. Then there's the functional testing, which is basically takes a game, run it, and check if there are problems or even regressions. But for this part, Pierre-Luc will explain it.
Thanks a lot. So I'll be quick because we're running out of time, but it's just a quick follow-up from last year. So a couple years ago, we kind of kicked off an internal test suite for our own consumption. This one approaches the problem from the other side, right? We don't do unit testing. Instead, we only test traces from real Steam games. So the main purpose for us is, to determine if a driver is good to ship or if it's going to regress any games. We also do performance testing, but it's not a benchmarking suite. Since it's trace-based, you can't really rely on the number that it's going to give you to be useful for what you would get on your own machine running the game. Instead, the number is only useful relative to previous numbers. So last year, I talked about opening the results to the public. And also opening the possibility of pre-release testing. So people have been able to submit their own branches for advanced testing. But we also test all the point releases. So here's some progress we made since last year. We have a performance dashboard. It's pretty dark here. You can see our hardware configurations there. We also added Nvidia configurations that should show up soon. We've been testing internally with them, and it's actually been really useful. So we're also opening up these results to the public. So this is a quick kind of at a glance, performance number. You see all the point releases that have been tested on the left. So all that stuff is open to the public now. You can browse to that. Share.Linergy website and comb through the results yourself. So one of the big things since last year is we've added Vulkan testing. VK Trace wasn't quite up to speed this time last year, but we've been pushing on it hard. It's really important for us to start testing it. There's more and more games that are starting to rely on it. So same idea. We're still ramping up test configurations, but it's coming along. If you want to do your own testing, your own pre-release testing, there's a new test run page. You can throw your repo if it's a GitHub branch or whatever. Throw in the SHA there. You can run a subset of the test. You can pick a subset of the hardware configurations. and you can request that your results be private. You'll be notified by email, or just have them up in the public as another test run. One of the changes we've made, from feedback is that now the test results are can be compared against any other test results. So there is a maintained baseline where someone will come through the results and call a given thing golden based on no regression. So you can have an at-a-glance result from whatever is the latest release that was tested successfully, but you can also compare to previous releases yourself. And you can do image results. That actually one of the main things that we test for regressions. It tells you the pixel diff, so you can get an at-a-glance idea, or if it's just a sampling error around edges, or if it's a major thing. And there's various visualizations to browse through the results. Again, all that stuff is accessible. You can browse to it and go comb through these results for existing test runs right now. Performance results are same idea. We loop one frame repeatedly. We get a number. Again, it's only useful relative to previous numbers, but it's really useful to find regressions, both on the CPU side and GPU side. So that's it. Thank you.
Any question?
I guess questions?
Yeah.
You mentioned rebuilding based on when dependencies change. I wonder, how do you guys know strictly the dependencies? For us, a small change to libdrm can mean we have to rebuild everything, or a lot of times there's some kind of dependency between, like we have to update X to have it work with new patches to Mesa, or especially in the Vulkan sphere, there's tons of dependencies between these little tools that commonly break. So when you get a check-in to GLS Lang, like, how do you know which Docker images you have to go and rebuild?
So Juan's going to answer that one, but in general, I've been diving through libdrm and X and back and forth, and I'm mostly aware when breakages happen, and I try to ping individuals. Would I build like driver specific or general distributions, so they always make sure things are updated? But you're right, we should have some clearer information. Juan?
Yeah. Also, this is worth to know that this dependency list is hard writing in the Docker file, so it's not. The system is not guessing what is the dependency, but it's like in Travis. You have the list of software, and you have the list of versions to build, and we do the same. And the thing is that if just when we build and there is a broken thing, we just check, okay, this was because now we need this version, so we update it. But it's not done automatically. It's to avoid to repeat installing all time the same version of the same of the package, the same version of the dependency, just avoid that.
Yeah, it seems like that would be really good to, if you could automate the dependencies between the Docker images so that you get the right one, and especially if you want to go back and test a stable branch, you need to have the right prerequisite images working together. I also wonder about I/O. How does it sounds like you have separate Docker images maybe for Piglet and then for Mesa, and then you can the different test systems can pull them down independently, so you don't always have to get a new Mesa when you get a new Piglet image. I wonder how the total I/O profile compares to just building and deploying a build route to the system.
I'm not sure I got the question. So you mean how we know which version of the image to pull, or? Well,
I guess when you have Docker images with the binaries that you compiled, is it much worse or different from like just rsyncing over your built files? This is what we just manually move files between the systems for test, and I wonder how Docker affects the the file I/O between your builders and your testers.
I don't think I'm getting the question really. The quality of sound is very bad.
Are you interested why he's using Docker as opposed to, let's say, rebuilding it locally every time, or rsync, or any other means?
Yeah, I'm considering using Docker myself.
Why
I'm wondering, the big bottleneck is I/O to the system, right?
We are not rebuilding because, in our case, the hardware are quite limited in the speed and the memory. And we noticed that every time we want to try to test, we were doing before using cron tabs in the night, it would take a lot of time building, consume a lot of space in the disk. And as I said, in a couple of times, we noticed that, oh, there is here, this works, and here, but doesn't work there. Okay, maybe it's the hardware. No, it's not the hardware. It's because there was a library installed here that was getting a feature that is not in the other place. So basically, the thing is that, okay, with this system, we can buy for testing only cheap devices, cheap hosts with different cards, stack them, and that's used as a test system. The build, running the build, which is quite a CPU demanding, is not going to happen here. So we can't use systems that are with very low powerful, only the power required to run the tests. And also we can just go there, drop all the image, and have the system clear. So we are messing up with the system with the distros installed locally, with the dependency we need. Basically that's the point.
And so finally, one of the problems I have is testing end-to-end compression, because the dependencies in X that we don't have in the distro we use. And so do you guys build X or up-to-date versions of X and deploy those in containers so you can test that as well?
Yeah. When I was explaining the here, let me. Okay. Don't know how to go back. Anyway, when you install the Docker runner, one of the things as I said, you install the mount all the requirements to run to get access to the hardware, to the graphics hardware. Well, another thing we use is just also mount all the required things just to get access to the X.Org running or Western running. We have probably we have a different version. We basically we get the X running in a container and then link both containers. But right now, as we are only using the X for testing, we just mount all the links required inside the test image. So basically, it means that when you run the test, it's running against the X, just running outside in the host itself. But yeah, even you could run the X in the different container, because the ways if something happens, like the X broke or whatever you are test, in the next step will be restart the container with the X or with Wayland, whatever you want to use, and then link both together with by mounts on these features that Docker has, like mbars or something like that.
Any other question?
You do a lot of testing in different hardware and so on. Do you get lots of false positives, like tests that are failing now after some change, but the test is buggy and so on, and makes you waste a lot of time? And if so, do you have any ideas for how to improve the test reliability? Okay,
so the question is if when running we have some failures and then it turns out that there are false positives, right? Yeah, yes, it happens a lot of times. And the thing is that in this pipeline, we have like a filter where we just remove all the tests that are, there are tests that takes a lot of time, like sometimes I found tests that takes 10 hours to run. There are other times that there are the flaky tests that today works, tomorrow doesn't work, and it's like, whoa. And the thing is that this is not a test system. We only want to have a minimum quality just to submit to the Intel CI. And the Intel CI is probably handling this better than us. So we just filter those tests. So yeah, at the first we were having those problems, then go to the machine, say, okay, this test is quite problematic, mark it as don't execute it because it's really creating, and then only keep a sanitized version of the tests, as a group of sanitized tests, just to use it. So it's done in the test suite. One of the things that, okay, don't test against these tests.
If you want BKCs on this, how to handle flaky tests, please come to the testing workshop. I'm going to talk about this because for IGTN on Intel, there's a lot of them. So we dealt with them pretty effectively and managed to actually fix them because flaky tests need to be fixed also.
Hi, my question is about if you are aware or know about some implementation, let's say for the inspection of the output of display done automatically by means of optical recognition, because in some cases you may have very good test results, but then you can have or see glitches, say in video or artifacts, and they are not always visible in the test result, maybe piglet or CTS. And I wanted to ask if there is some open implementation that can help, and if it could be integrated in this testing process. Thank you.
Right now our test system is quite simple. I mean, it takes a lot of jobs, but it's quite simple. It only uses piglet tests. So if there are things like, this is an artifact here, and piglet can detect it because for piglet is a pass, for us it's also a pass. I hope that probably in the Intel CI system they can detect these kind of things. Or the other thing is that you can probably detect these things maybe on the LunarG system, that besides the performance, it shows you difference and you can see for it in games like, this is not rendered correctly. Supposedly, this should be detected when you run Vulkan tests and when you run OpenGL or Vulkan, depending on the game, are using piglet. But I mean, there are corner cases that maybe it was covered by a test and shows up in the game. But of course, this is a much simpler system, so we don't detect it.
We're running a bit out of time. Maybe time for last question. Anybody? Okay, remember there is a workshop just after lunch related to the graphics testing. Thank you very much. Thank you.